Hello everybody. In the following, I'm going to present recent work on action recognition in videos. My name is Cordelia Schmid. One task of automatic video understanding is the classification of short clips. For example, given a short clip, we want to assign labels such as answer phone or handshake. Another task is the classification of activities such as birthday party and grooming an animal. However, if we want to understand the videos more precisely, we need to localize the person and its actions in the video. This is of particular importance in the context of self-driving cars, where we want to know where the pedestrian is, what is its actions, and also predict what it's going to do in the future. Another application is video surveillance, where again, we want to know what each person in the video is doing, and if there is some action which is dangerous. Finally, the ultimate goal of video understanding is to obtain a complete description of the video. And to do so, we also need localize precisely the actors and their activities. So here, for example, we see we would like to obtain, as the head waiter takes them to the table, they pass by the piano and the woman looks at Sam. Sam, with a conscious effort, keeps his eyes on the keyboard as they go past. The head waiter seats Ilsa. So here we really want to know what precisely is going on in the video, and to do so, we need to localize the people. Why is this a difficult problem? Actions can appear in a large variance of appearance. We can have viewpoint changes, interclass variation, and camera motion. Compared to objects, action can have larger interclass variations, and the camera motion plays a more significant role. Furthermore, manual collection of training data is difficult. There are many action classes, and many of them only occur very rarely, which makes finding when annotating them more difficult. Furthermore, in many cases, we would like to annotate not only the action, but also the interaction with objects and other actors. Finally, the action vocabulary is in many cases not well defined. What is the right granularity, and how do you represent composite actions? In this talk, I'll present some of our recent work on spatial temporal localization of action recognition, then move on how to improve the model further by modeling spatial and temporal interactions, show how this can be used for action forecasting, and conclude with some recent work on behavior prediction for self-driving cars. Spatial temporal action localization requires localizing the actor and the precise moment in the video where the actor is performing an action. So here, for example, we can see that in the first row, the action drinking is localized precisely, and in the second row, we can see that the action brushing teeth is localized precisely. State-of-the-art approaches first localize potential actors in individual frames and classify them. They then track these actors over the video, score them, and localize the precise moment in time where the action is performed in the video. Looking at individual frames individually makes the fact that actions can be ambiguous. If you look at the image on the left, we don't know if the person is sitting down or standing up. However, if we have several frames, we can see that in the first case, the person is sitting down, and in the second case, the person is standing up. So what would you like to do is to model not only the content of an individual frame, but model the activity or the action over a joint set of frames. What we do here is we represent initially the actions by anchor cuboids, which have a fixed spatial extent over time, and then regress these tubelets to deform it to the shape of the moving actor in the video. We then also can score these tubelets and show that we get an improved score. The approach we use here is based on a state-of-the-art object detector, which is SSD. SSD has a consecutive set of convolutions obtained at multiple layers, which you can see here in yellow, red, and purple. We obtain such a representation for each frame in the tublet, where the anchor boxes correspond to the spatial location. We can then combine the obtained convolutional features in the final layer. And this final layer has an additional classification and regression head, which regresses the individual positions, individual frames, and performs the classification over the entire tublet. We evaluate our approach on two datasets, UCF, where we 24 actions in more than 3,000 trimmed low-resolution video clips. Actions are sports actions and everyday actions. And we also evaluate them on the more realistic ABI dataset, which has 80 actions, 300,000 movie segments, where we can see that there can be multiple actions in each clip, which makes the task more difficult. If we look at the video MAP results on the UCF 101 dataset, we can see that our approach outperforms the results for all overlap thresholds. The overlap threshold measures how precisely the action is localized in the video. So 0.2 means that the detected action and the ground truth action overlap by only 20%. And we can see that as we increase the overlap threshold, the performance goes down. But we can also see that the relative improvement of our approach compared to the state of the art goes up. And this is due to the precise localization with the action tublet. If we look at the results, in green, we can see here ground truth, and in yellow, correct detection. So we can see here, this example, that the action riding horse is detected correctly. Here we can see that the action jumping is directed correctly. And we can see also that the corresponding actor, which corresponds to the action, is localized very precisely in the video. Here another example, which is skiing. We can see that the actor is detected very precisely. Action tubelets over time are linked together to consistently find the action in the video. Another example, bike riding. Let's see here and here, trampoline jumping. Again, the motion of the child is followed precisely by our model. And if we now look at two failure cases, the first one localizes the action incorrectly in time. And in the second case, we have two actors interacting with each other. And this is a failure case because our model only models one object at a time and doesn't model interactions. This brings us to our next work, which then attempted to model the interactions of this one person with this environment, either other people or objects. If we look at some of the failure cases on the ABI dataset, we can see here on the first example shows an example where the man first follows alarm for handshake, but what the person is really doing is reaching out the arm. And what we would need to model is also the action of the second person to see that the second person is also reaching out the arm. The next example is a false alarm for smoke. What the person does, the person is covering his mouth, but there's no cigarette in the hand. So again, if we had a model which shows that there is no cigarette present, we could avoid this false alarm. And the final alarm is a false alarm for riding, but the person is looking down. In order to model the interaction of the human with the environment, we have developed a structured model for action detection. This structured model first extracts actor tubelets. It detects humans in the individual video frames and links them together to get these actor tubelets. In parallel, it also constructs object tubelets and then associates the objects with the actor tubelets. And then you can model, for example, actor 1 is talking and holding an object. So we can see that the actor 1 is talking to another person and at the same time holding an object. The temporal dependencies are learned by constructing tubelets based on the appearance similarity of the actors. Here we use a Siamese network and a triplet loss. So this gives us a set of individual humans linked together, and then we learn how to combine the individual features in these tubelets with graph convolutions. Second, we model how these tubelets interact with each other based on human-human and human-object interactions. We have a soft assignment which integrates the features into this model. The model is based on graph convolutions. If we look at the quantitative results, we can see that our baseline in the third row obtains an MAP of 16%. Competitive approaches obtain 20%. And then if we add the actor tublet model, that is just the temporal interactions of the different moments in time, we get a 5% improvement. And if we add also the interactions with the object, we get a further 1% improvement. Why are the results still relatively low? This is due to the fact that we don't have for many classes enough training data and that the models the interaction models need to be still improved. This is ongoing work. Here an illustration of a failure case. We can see here we obtain an incorrect label for sit. So basically, as the motion goes on, A, the box doesn't follow the child anymore. B, it cannot detect correctly the child is falling down. And see here, if we apply our temporal approach, we can see that we obtain the correct label for sitting down. So here one more time, we can see the child is falling down. Another example here on the left, we only use the basic model where we only model the action of the person. And then the predicted action is hold because the hand is holding something. However, if we have our soft relation graph, we can see that the person is interacting with the fork, and we can then predict the action eating. Once we have a model which takes into account the relation with the environment, we can also use it for action forecasting. What we want to do is to predict the action. So for example, the example on the left, should I cross the street or should I wait? Example on the right, what is going to happen? Is the child going to fall down the stairs? And here a few other examples. They're sitting and talking, or what is going to happen next. You can see that they're glasses. So the next step, what they're doing is they're going to clink the glasses. Similar in the middle, the woman is holding and standing. The next action, which is performing, is serving. The last example is hugging and standing. And the next action they're doing is kissing. So what's the idea? We have the past actions, the present action, and we want to see what's going to happen in the future. So in the example on the left, we can see that the woman is riding the horse. Then she stops and talks. And then what's the next thing is she can predict that she's going to get off the horse. The model we have developed is based on an action proposal network. So we have a set of proposed regions for which we extract the visual features. And then we have a model which models the interactions between the different objects in the image. This is based on a graph neural network plus a recurrent network, a gated recurrent unit network, which models the actions over time and predicts actions in the future. The edges of our model are learned by an attention mechanism. If we look at the results of action forecasting, we forecast actions at step 0, 1, 2, 3, 4, 5. We can see that if we just, let's look at the last column, t equals 5, if we just predict the actions based on the last current and no interactions, we get a performance of frame IP of 3.6. And then if we add a recurrent network, we get a further improvement. And by modeling the interactions with the environment, our performance increases further. Why are the results still relatively low? This is due to limited to failure cases of detections and interactions. If we look at a few results here, you can see the video up to frame T. We forecast the person is going to eat, because given the posture of the person and what he's holding in the hand. And then if you look at the subsequent frames, you can see that effectively the person is eating. So we have correctly predicted the future actions. Next example, here again, the video up to frame T. We forecasted the person is getting up, because we see he's getting in the movement of pushing his hands on the chair. We can see here that effectively, if you look at the subsequent frames, the person is getting up. Similar here, example where the person is, we forecasted the person is reading and the person is effectively reading. Another example is that the person is going to open the door. If you look at the subsequent frames, the door is correctly opened. Now, if you look at two failure cases, in the top row, we predict that the person is getting up, but for now, the getting up action is not yet happening, so it's the wrong duration of the forecasting. And then in the bottom, it predicts closing the door, but they're opening the door, and this is due to the fact that in several cases, multiple futures are possible, and this means that for future work, we need to predict not only one action, but several actions with corresponding probabilities. Last, I'll show some recent results for behavior prediction for self-driving cars. This is joint work with Waymo. If you want to predict the intent of a vehicle, for example, here we see we want to predict that the vehicle in white is going to turn in the crossing left, we need to understand the scene and the dynamics. That is the behavior of the vehicles. So here we see, given the model of the crossing and that the car is advancing on the lane, which is turning left, we can predict that the car will be turning left. Existing approaches mostly operate on the map and the trajectories of the vehicle. However, this and encode them with a convolutional neural network. However, this is costly in computing memory because we have to store the map and run the convolutions over the full map information. The approach we propose here is encode the map in a more schematic representation. Basically extract the vehicles and then each vehicle trajectory is represented by an arrow. Similarly, the lanes are encoded by splines and so forth. So what we propose here is to not work on the full map with CNNs anymore, but to introduce the Vectornet approach. And this approach represents the map and the agents simplified as points, for example, stop signs, polygons, for example, crosswalks, and curves, trajectory, or lane boundaries. Each of these entities is represented by a polyline, and each polyline is then cut down into vector fragments, where each vector fragment is represented by the start and end point, and the corresponding feature. We can then represent each polyline as a subgraph. So what we then have, we have the whole environment, which is the map, and the agent represented by a set of polygon subgraphs. So here on the left, you can see the input. The input we have taken a full environment. For example, the crosswalk is represented by a polygon, the lane by a spline, and the agent as well. Each of them is cut down into vector fragments, and each of these vector fragments is represented by a polyline graph. Then we have the set of polyline subgraphs, which each builds up on the set of vector fragments. And we can then combine these polyline subgraphs in a global interaction graph, which exchanges the information among polylines. Local graphs are encoded with multi-layer perceptrons, and the global graph with the self-attention. For training, we use supervised training based on a large number of example sequences. So we have a large number of example sequences which were culture driving around. We use this to train our model. We have two complementary losses. First is the target loss. It's an L1 loss for trajectory prediction. Just measure if the trajectory is predicted correctly or not. And the second is a map completion loss. We mask out random graph features, as we can see on the figure right. And then we have to predict the masked out features. So this is similar to the loss which is used in the BERT model. And what does it do? It enhances the understanding of the scene. Because if, for example, something is occluded, we still want to predict it correctly. If you look at the experimental results, we report performance on the Argoverse motion forecasting dataset. It contains 333,000 5-second long sequences. They're split in train, val, and test set. Test set is held out and can be only validated on the server. It includes vehicle trajectories and map information. Here we use from 0 to 2 seconds as an observation and from 2 to 5 for predictions. So we measure the prediction accuracy at each second, and the history trajectories are obtained with automatic perception systems and thus noisy. So it models the current driving systems accurately. Metrics are average displacement errors in meters computed over the entire predicted trajectory, and then displacement errors at individual time frames, also in meters. If we look at the different components of our model, we can see if we just take the path trajectory of the target vehicle and use L1 loss, we obtain 5.2 meters error at a displacement error at 3 seconds. If we then add the map information, we reduce the error. We reduce the error even furthermore if we use the other vehicles, and you can see that by adding the map completion, we get a further improvement of our model. And if we compare the state-of-the-art convolutional architectures, which we have here implemented with FreeSNet 18, which is standard, we can see that our model only uses 20% of the compute when there are 50 agents per scene. We have 29% of the parameters and an 18% better performance. So our model is has better performance, and B, as we claimed in the beginning, it's significantly more lightweight and can hence run faster. If we compare the state of the art on the Argoverse forecast test set for a number of sample trajectories equals to 1, we can then see that our approach outperforms the state-of-the-art performance. These results were obtained on the 18th of March, 2020. In conclusion, we have shown that our approaches obtain excellent results for action recognition and behavior prediction. We've shown that the introduced models, which take into account spatial and temporal relations, allow to improve the performance. And we've also seen that it's important to have sophisticated models based on graph convolutions and self-attention. Thank you for your attention.